Okay, welcome back to Introductions to Computer Networks at NTU. This is Polly once again, and I see that many of you are popping in. In the meantime, we start the lecture today. So, Yu Zheng and Jun Han, welcome back, and let's go over the assignments due this week, okay? So we have PA5, which should be straightforward once you're done with PA4. Okay, all we need to do is just to make your server now loops, okay, forever. Okay, so it would be like the real servers that are waiting for a client to connect. A little bit more like a real server. After PA6, it will be a full-blown server. Okay, and we have 4 quizzes due this week. Okay, and guys, exam 1 results will be out tomorrow at 1 p.m. And Polly needs to say that this semester, you guys are exceptional. Okay, let me just give you the median score ahead of time. It's 97 points. Okay. Polly felt that she made a mistake giving a simple exam, but in fact, it is not simple at all. Sorry guys, Polly is just completely puzzled. How come you guys managed to complete a long exam with the programming problems and complete them all within a limited amount of time and get most of them right? I just don't know, okay? I'm so puzzled, okay? Last year, the average is about 80-something, median also 80-something, and the semesters before this semester and last year are in the 70s. But this time, the exams are actually harder than before, even harder than the last time. So I'm just so puzzled. If you guys can offer me some information about how come you're able to finish all the questions and achieving an average of 97, okay? So hey guys, this is just unbelievable. I'm sorry, median. Actually. Yeah, I think the median is 97. Maybe 95. I probably couldn't recall exactly, but it's high 90s. Okay, so tomorrow after you get the report, and if you can offer me some tips on how you find the exam simple, not challenging. Okay, let me know a little bit more how you feel about the exams. Okay. Good. So that is just something that is Polly's crying for help to make sure that I can kind of differentiate you guys. Because then I have a bunch of students. You guys will all be equally good at the top. It's really hard to grade on curve according to the university's instruction this way. So I would need to know how I explain if eventually I need to give a not so normal grade distribution at the end of the semester. Okay, guys? All right, now back to the lectures. Today is going to be straightforward. Not exactly simple, but straightforward. We have just 2 topics. We are still talking about the reliable data transfer. Okay, and then we begin to talk about these we begin to talk about this particular function or a series of mechanisms to address and to provide the function using sort of more technical terms, okay? So we have finite state machines, and we use kind of pseudocode-like way of describing the transitions, okay, of a finite state machine. And we've ended up introducing the RDT, RDT to up to version 2.1. Today we'll continue. Okay, the first machine is 2.2. This one, the mechanism is identical to 2.1. Okay, all that's different is instead of sending ACK packet, okay, from the receiver side, such that the sender, upon receiving the ACK packet, recognizes that the packet he or she is sending, okay, is well received. The receiver might also send NAC packet. That way, the sender would know that, hey, whether a retransmission is necessary. But in RDT 2.2, let's try, instead of sending two kinds of packets, ACK and NAC, we send just one packet. Okay, we use one packet format to represent two kinds of packets. All right. So this is describing the mechanism. That's the idea. That's about 3 minutes. RDT 2.2, it's essentially the same as 2.1, except here. It's going to be the NAC-free version of 2.1. By saying that, what I meant is, well, in 2.1, when the packet arrives at the receiver, okay, we send positive acknowledgement, that is ACK. Well, in case that data packet is corrupted, we send a negative acknowledgement, that is NAK. Now, as a result, we do have like two packet formats, right? One says I am acknowledgement, the other says I'm negative acknowledgement. So RDT 2.2 here is essentially to say, let's not have two different packet formats, just have one acknowledgement packet, but add a bit in the acknowledgement packet, and we change the bit, okay, the value in the bit, to indicate whether it's really a positive acknowledgement or a negative acknowledgement. All right. So same functionality as 2.1, but using only ACK packet. But the ACK packet will be carrying an extra bit. That is also the sequence number. Okay, so that is the sequence number bit. Okay, and the value in the sequence number bit is going to tell the sender whether this is a positive acknowledgement or a negative acknowledgement. All right. So now we have, a NAC-free protocol. Receiver sends acknowledgement packet for the last packet received. Okay. Think a little bit about it. So the receiver starting from waiting for call from below 0. Right? So if packet 0 is received okay, receiver here sends acknowledgement for packet 0. Because packet 0 received okay. The last packet received okay is what? Sequence number equals 0. Now, go to wait for call from below, packet 1. So if packet 1 arrives at the receiver and it's corrupted, what does receiver do? Which packet is the last received being okay? Well, 1 is not okay. So, still sending ACK packet, but sequence number bit there is 0 again. All right. But at the sender side, what's going to happen is sender will receive the first ACK with sequence number 0, right? Indicating packet 0 is received okay. But sender there is going to receive another sequence number 0 ACK. Ooh. Hey, how come I get acknowledgement for sequence number 0 twice? Yeah, having duplicate acknowledgement at a particular sequence number that indicates the next data packet that sender just sent out was corrupted. A negative acknowledgement in a way. So receiving duplicate is essentially signaling, sender is sending a NAC, right? So sender there will have to what? Retransmit the packet that's last sent. All right, so the idea is to check whether an ACK is duplicate to decide whether this is a packet that's new and well received or not. Okay, good. Now, let's go through the finite state machines of RDT 2.2, but this time we'll do it this way. Having seen the finite state machines a few times already, so what we will do is to try to convert from RDT 2.1's finite state machine and see if we could adapt from RDT 2.1's machine to RDT 2.2. Okay, and let's start from the receiver side of finite state machine, which is slightly easier. Now let's try to develop RDT 2.2's finite state machines. So here what we will do is to borrow from 2.1 and start from the receiver side of the finite state machine. All right, so initial state is wait for 0 from below. So we're expecting data 0, and we get 1 if it's not corrupted and indeed carrying sequence number 0. Then we extract data, pass it up to the application layer, generate an ACK packet with the checksum, and then send it out. Now, if it's 2.2, we'll be generating an add packet, all right, but this add packet should be carrying a sequence number, isn't it? And according to 2.2, the sequence number should be the last data packet received OK. And what is the sequence number of the data packet received OK? Well, we just actually what? Received 0. So, yep, you're correct. The add packet we're generating here for RDT 2.2 should carry sequence number 0. And so once we finish all the actions, we'll be finishing the transition and move to the next state, wait for 1 from below. And if we get packet 1 coming in, passing these conditions, so indeed carrying sequence number 1 in this data packet, then similarly, we take the data out, generate ACK, and send it out. And here, the ACK sequence number will be what? Data 1, the sequence number that we just received. So as a result, we could actually conclude the receiver side of RDT 2.2 should look more like this. And I'm ignoring the upper right part of the receiver's finite machine. So receiving a packet, not corrupted, carrying sequence number 1. The add packet will be generating, of course, it needs to be an add packet format, carrying checksum. It also carries what? The sequence number of the data we just received, OK, and which is 1 here. So for this other transition at the top, then it will be make packet 0 ACK checksum. Now, hey, the receiver side of RDT 2.1 actually have all these other transitions, right? So we only handle this part and extend it to 2.2. We will still have to extend these transitions so that it will work for 2.2. Now, these are actually exact mirror of each other, so let's just focus on one side. Okay. Now, let's pick this transition first and see if we could evolve it as well into 2.2. So this is receiving a data packet, but it's corrupted. So in 2.1, we send a negative acknowledgement. But for 2.2, we don't send negative acknowledgement packets anymore because we don't have that format. Instead, we send ACK. But we have to carry a specific sequence number to indicate whether this is really a positive acknowledgement or a negative acknowledgement. So, the rule of thumb generating the sequence number there is what? Who is the last data packet received OK? Now, receiver is currently waiting for data 0 coming from below. So what that means is that the last packet received OK should be carrying sequence number 1. So ACK here should give the sequence number of the data packet last received OK. So yep, it should be ACK1 here that we're sending back to the data center. Now, what about this other transition? Receiving a packet, not corrupted, but carrying sequence number 1. This is not the data 0 we're expecting. All right. How can this be happening? So this is the very odd situation where the previous data, ACK, being sent back to the sender gets corrupted, if you recall. Add packet or negative acknowledgements can be corrupted now, right, in version 2. Now, if negative acknowledgement is corrupted, sender simply retransmit, no problem. But if positive acknowledgement gets corrupted, sender also retransmit. And that is this odd situation here. You already sent back an acknowledgement for data 1, and yet it's receiving data 1 again. Yep. So this is the situation. Add packet gets corrupted, and so you're receiving a duplicate of data 1. So we do not extract data and pass it up to the application because that's going to repeat words, repeat letters, repeat sentences. Okay. So we only send back ACK. And this ACK should be what? Acting the last packet received OK, therefore also carrying sequence number 1. Okay. Now, if you look at this guy and this guy, both transitions, the actions they'll be taking will be identical now, right? Both sending acknowledgement packets carrying sequence number 1. So then perhaps we could just combine the two transitions. Receive a packet from below, checking if it's corrupted, or carrying sequence number 1, send ACK packet 1. Right? And you know what? ACK packet sequence number 1 is already being generated here. Send PKT, if you do not replace this variable's value, it will remain the same. And so if we just simply call this, then we just combine the two transitions and make it very brief, like this. RDT, either corrupt or carrying sequence number 1, simply send back the send packet that has been generated here, which is an ACK with sequence number 1. All right, so you see that not only the RDT 2.2 makes just one pack, requires just one packet format, but also that some of the transitions can be made more compact. Okay, so you see an example in the receiver. Now let's check out the sender side of finite state machine. Similarly, we'll try to convert from RDT 2.1's machine to 2.2. Now let's try to develop the sender's finite state machine. Again, let's borrow 2.1's sender finite state machine and start from there. This is the initial state. We wait for call from above. And if there is 1, then we generate starting from packet 0. And then we enter that wait for ACK state. Now, in case a NAC is in, we do have this is NAC check, isn't it? Okay. So if that is the case, we retransmit the data. Otherwise, everything is fine, and this is a positive ACK, so we do nothing and move to the next state and gets a call again from above. But the thing in 2.2 is this. Well, there's no such thing as negative acknowledgement packet. In fact, both negative acknowledgements are just ACK and carrying different sequence numbers. So this will also be a is ACK check, okay? But the difference is going to be the sequence number they are expecting being different. So what should be the sequence number we expect here to pass so that we move on to the next state? We are expecting 0, right? So the sequence number here should be carrying 0. So we should be checking is ACK and particularly sequence number being 0. Therefore, we can move on. Send the next packet. If everything goes well, we should be getting another ACK packet, then carrying sequence number what? 1, because we just sent out packet 1, right? Now, the NAC here, check can no longer be valid and will be also doing the is ACK check. But what should be the matching sequence number here to trigger this action? Well, we just send packet 0. If packet 0 was corrupted, the receiver would be what? Sending the last data packet received OK. So that should be what? Sequence number 1. Similarly, for the check here, it should also be is ACK, but sequence number what? 0. And that takes us to the sender side of the finite state machine. So we change this line as well as this line. So this line is what? Expecting 0, so check whether the sequence number equals 0. This is also now is ACK, and this should be carrying sequence number 1. All right, so that was RDT 2.2, and we're done with version 2 of RDT. Before we go on to RDT 3, let's work on this quiz. Okay, so this is quiz 19. It's called The Lord of the Ring because it's adapted from a fantasy novel, okay, one of Holly's favorites. I don't know if you have read them, but let me describe the scenario here. Okay, so this is the Battle of the Helm's Deep. So Helm's Deep is here in the middle of the map here. So the fantasy happens in Middle Earth. Okay, so that is a fantasy world, obviously, and Helm's Deep is right here. And hey, Saruman is a dark wizard. Okay, so this dark wizard is pure evil. Okay, so he's gathered and fostered a big troop, okay, of all kinds of creatures, okay, powerful creatures. And the troops are pushing into Helm's Deep. Okay, so Helm's Deep are these horsemen people. They call themselves the Rohim. Okay, and King of Rohim knows that, oh, big trouble. Okay, and starts calling for help. So the king sends a messenger to call for help from Gondor. Okay, so Gondor is another tribe of humans. Okay, so Rohim are the horse people. Gondor are just Middle Earth people. Okay, and Gondor is right here. Yeah, down here. All right. And the messenger is sent from Helm's Deep to Gondor. So you can imagine that the messenger will be crossing this place called the White Mountains. Okay. Unfortunately, the White Mountain is full of this thing. The orcs. Okay. What's really horrible is that these orcs eat people. Okay. People like the messenger. Okay. So the messenger might get lost. Okay, or eaten. Now, guys, I ask you to role play Gandalf the Wise. Okay, Gandalf is a white wizard, okay, who like to be friends with all creatures and be wise. Well, you have to be open-minded to be wise, okay, I have to say. So Gandalf the Wise, guys. Okay, there are so many of Gandalf the Wise, okay, for the next few minutes. How can you make sure that Gondor gets the call for help? Okay, with the messenger might be eaten by the orcs in the middle of the way. Okay, so let's go to the Discord space and Polly. Okay, yeah, upload the quiz over there, guys. Given your capacity, capability, you are only allowed 5 minutes. Okay, and by the way, as well, given that the quiz is based on a fantasy, so your solution can be also a fantasy. But in case those who are more practical, feel free to come up with solutions that will be practical to implement in real human world as well. All right, so guys, 5 minutes. Let's start counting time. Okay, so guys, feel free to go on and think a little bit more. But I see that some of you have already provided what you think, okay, will be a good solution. So let's go over these as you guys are still pondering, okay, or formulating. So team 6 here, Han Yu says, disguise the messenger as an orc to avoid conflict, right? So you see that the orcs eat people. What if the messenger doesn't look like people? Okay, so it seems that the target is specific, focusing on specific type. And you exploit that part of the formulation of the problem. Okay, interesting. Let's see team 3. Send flares to the sky so it can be seen from far away. Yeah, so this is actually the solution in the novel. And this is what? Wireless transmission, isn't it? Yeah, visible light is wireless. Transmits wirelessly. Send many messengers and there's some of the... Oh, okay. Send sacrifices or decoys. Yeah, and once the orcs are fed, then the real messenger gets through. Well, this is a very costly solution, but it works. Okay. There, jukebox for team 3. Thank you, Dorothy. And we have team 7, Yixing. Just broadcast the help message loudly again. Oh, okay, this is very interesting. Team 7. Okay, hey, we have a very wise Gandalf this here. How about just spread the words? Like spreading rumors. Rumor travel really fast. So pass the message on to all creatures, right? And asking all creatures to spread the words. And I think chances high that the message gets to Gondor somewhere. Team 2. Try sending a pigeon with a scroll to avoid alternative path, right? Instead of crossing the mountains. And orcs obviously don't fly, right? And pigeons will be definitely traveling another channel, right? That the orcs won't be. And I will send a green pigeon back. Interesting. So a pigeon somehow to differentiate, okay, a returning message, and that is that can somehow be differentiated from the sending pigeon, and that would signal as an egg. Oh, and a red pigeon will act as a neck. Very interesting. Okay, and this is probably possible, right? Being a wizard. Can cast a pigeon with a different color. Cool. So that's how you encode egg and egg on pigeon. Very interesting. Let's hope we send. Oh wait, yeah. Let's hope we send green pigeon. Okay. Of course, Gondor can send a negative acknowledgement, right? Refuse to help. And I don't know whether it's a good thing or a bad thing to help or participate in a war. But okay, I'm not wise enough to answer that question. Okay, guys, I believe that you guys will be all wiser than Polly, given a few years. All right, Yu Zheng, let's see. Pretend to invade the orc tribe. Oh, yeah. Yeah, it's a decoy, and this is a legit decoy. Yeah, I think some of the big scams work this way as well, right? Some of the robbery heists work this way as well, right? They distract the police and the fire department as they, break into a bank. I see very diverse answers coming out of you. Guys, I'm so very pleasantly surprised. Let many warriors go with the messenger. How to protect them, of course. Yeah, so you kind of set the messages to some priority so that it's hard to take off the network, isn't it? That's to strengthen, okay? Yeah. So you mean providing muscle, right? Sends a messenger or a moth every day. Oh, okay. Again and again and again. Until a messenger returns, okay? Interesting. Junhan, you have a very robust and potentially sort of low delay solution. So guys, I need to break early a little bit talking about IDT 3.0. In 3.0, you send a messenger. And you see, ROM here, we need to wait, right, for a reply. And that can take a long time. And by the time a return message is received, Saruman's troops might be in Helm's Deep already. Okay, so keep sending messages. Actually speeds up the process. Okay, in case one of the messengers is lost, the second one is coming right away. Because this is certainly another way, redundancy. Okay, to try to speed things up. Team 20. A flare gun Oh, so it's not just a flare. It's also there is also sound. So it's a oh, okay. This is hey, we do this a lot, right? We send data over multiple frequencies, right? Audio on one frequency, visible light another frequency. So you modulate the signal on multiple frequencies. That's another form of redundancy, but it's a concurrent redundancy. Wow, very clever. Okay, so this is an enhancement to, I think, one of the Team 3's solutions. Okay, very good. Choose longer, smoother, and further pass. Okay. So, yeah, so how about taking a route that just doesn't go across Y Mountain? And hey, Yingxuan, Ethan, this is happening on the internet. For I'm pretty sure that we, messages from Taiwan, would avoid passing the messages through the routers from China. And I think simply with all the regions that are in tension, that we configure our region-wide border routers such that the messages goes to the regions that are friendly to us. Okay, and hopefully that get routed through the regions without crossing the regions. Might be a bit hostile. Okay, so this is choosing another route instead of the shortest route. So longer route but reliable might ended up better. All right, guys. Aerial photo. Then we can figure out. Take a plane, of course. It's a fantasy world, right? But this is certainly a 21st century. We are already in 21st century, 22nd century. Okay. Oh, 21st century, not fantasy novel. Okay. Sure. So Team 10 is actually developing Team 18's solution further, right? So how about finding a detour? That will be longer for sure, but shortest among all the longer, safer routes. This is very cool as well. So I see in a way that you guys can build a solution on top of a earlier solution. You see again that perspectives is powerful. See? Guys, so if you are, solving a problem for real, definitely get yourself in a team or, get people in your team so that you have different perspectives. Through the territory of the so use beacons, hopping, and so it's a so these days we purchase wireless APs, okay, that will actually create a region that you allow all the machines to connect wirelessly to the AP. But in case you live in a huge house, okay, so that particular Wi-Fi area is not large enough, then you purchase a couple of these beacons, Wi-Fi beacons, that you connect them in a peer-to-peer mode, so that you expand the reach of the Wi-Fi network. Okay, so that is the solution that Boy was talking about. There you go. Now, in case you find, because in Taipei, the buildings are very often built with concrete and steel. So chances high that if you do 5G Wi-Fi strictly without the 2G, then you might need an extender, okay? You need another beacon to relay the Wi-Fi network. Yeah, Sing here says, send my message. Send many messages that would maximize the probability of at least one of them, okay, reaching Gondor, definitely. Okay, so this is also exploiting redundancy. King send messages, wait for the messages, have received the messages, send it again, and there you go, there you go. Yeah, good exercise of RDT 2.2. Make the mechanism simpler. Okay, and just keep sending it. So extending RDT 2.2. Very good. 预期, take a detour. Put the Yu Qi obviously have read the novel. Okay, yeah. So this ring is makes the subject wearing the ring invisible, and then you can traverse White Mountain without orcs noticing. Oh wow. Okay, fantasy story needs a fantasy solution. Perfect. 正南, try letting the messenger broadcast message loudly. Encrypt. Oh, okay. Interesting. So this is to develop the rumor solution further, right? And the rumor is also encrypted somehow only Gangdor people can understand. Okay, so whoever is repeating the rumor, they are just repeating the rumor, but they can be interpreted back. And Gangdor might realize that Roem is in trouble. So how about sending the messages in secret? That would definitely prevent the orcs from knowing and then leaking to Saruman, right? Oh, Ethan. There are many supporters coming. Okay, let's see. Invite the... Oh! Saruman and orcs to meet and fight each other. Wow. They get to Gangdor and prepare for a surprise comeback. Oh my goodness, Ethan. Hey, this is perfect. Okay, I'm gonna give you this. So 100 points here. But where are my 00? There you go. Oh, okay. I can only give you this. So maybe I can change it another way. Wait. So, yeah, I think we can always figure out another way of achieving what we want to do, isn't it? There you go. 100 points. Okay. Definitely extra points here, Ethan. And shown here, Gandalf can befriend various eagles. Yeah, eagle. Gandalf indeed knows many creatures. Okay, so eagles are definitely the group of creatures that Gandalf can exploit for the purpose. All right, great. So guys, now you know approximately, right, how RDT 3.0 might work. Okay, still you send message, but you wait for acknowledgements and see if the receiver end gets the message. Okay, so this video coming up next is long. First, Polly is gonna describe the mechanism, and this is by the way, if you observe in version 2 we assume bit errors only. Okay, and RDT 3.0 kind of addresses the issue where we have packet loss. Okay, and so bit errors and packet loss are indeed the kind of errors you might run into on the internet. Okay, the different ways of getting messages lost, and in a way that RDT 3.0 should be complete as a reliable data transfer mechanism. So this first video will introduce the mechanism, in the first part, but the later part you will begin to see the finite state machine of RDT, and particularly the sender side. We'll talk about the receiver side in quiz 20. All right. So let's play the video, 5 minutes. Now, the last version of RDT, the RDT 3.0. In version 3, we're going to make it very general. So there could be bit errors in the data packet, in the acknowledgement packets, but there could also be losses of the data packets or the acknowledgement packets. So the new assumption here is very general. The underlying channel might have bit errors, but it might also have packet losses, both at the data side as well as the ACK side. Now, all these mechanisms we have in version 2, checksum, X, retransmission, and the sequence numbers to avoid duplicates will help, but only help for, bit errors. So, in case of packet losses, not enough. So we need to add extra mechanisms. And the extra mechanism is this. The sender waits for some amount of time for the ACK to come back. If the ACK does not come back within the time window, then retransmit the packet. Okay, so retransmit the data packet if no ACK comes back within that timeout interval. All right, so what we're doing here is to require setting of a countdown timer per data packet being sent. Okay, so when the data being sent, timer gets started. That timer is going to tick. If ACK comes in before the timer expires, cancel the timer. If there's no ACK coming in and the timer expires, retransmit the data packet. Right? So that's pretty much all to address the packet loss issue. Now, hey, some of you might be wondering, what should be the timeout interval there, right? Hey, internet delay could be changing quite a lot over time. So these data packets can be just delayed, or the ACK packets coming back can just be delayed. So in case they are slightly longer than the timer that we have set up, then we will be retransmitting data unnecessarily. Yes, okay. Some of the retransmissions might be unnecessarily a duplicate. Just like when ACK is corrupted, the retransmission from the data sender in 2.1 is also unnecessary. But it's okay. We already have the mechanism right there, which is the sequence number. That's going to address the duplicate issue. So no worry, even though if we didn't set the timer quite right. It's just that there'll be a lot more unnecessary retransmission if the countdown timer is too short. All right, so hey, determining what is the duration for the countdown timer, that is also an art. We'll also see later in TCP how that is calculated, how that is estimated. All right, so sequence number is necessary again in RDT 3.0. The receiver needs to specify the sequence numbers for the ACKs, just like the data side needs to specify the sequence numbers for the data packets. And this is RDT 3.0 sender. Well, the usual technique, let me draw a line. So we just focus on one side of it, you'll see that the other side is similar. So what do we have here? Starting from the initial state, get a call from above, generate the packet, starting from sequence number 0, and what? Wow, we have these timer stuff, right? Starting a timer. And this is the transition next. If everything is going smoothly, receiving an ACK, it's not corrupted, and it's indeed ACK for 0. Then what? Stop timer. Now, if things don't go all that well, and the timer expires, then retransmit the packet and start the timer again. Because, hey, we just sent the data again, then the timer needs to be refreshed. Now, what is a bit unusual is in this transition. So what is this transition in 2.2? Well, the packet coming back from the receiver, if it's corrupted, or if it's clear that it's a negative acknowledgement, previously what did we do? We retransmit packet, right? Like calling UDT send packet here. But we actually do what? Nothing this time. Would that work? If it's corrupted ACK or a negative acknowledgement, and we do nothing, would that work? You know what? Hey, there's this transition, right? So sender here would just not work in case we get this explicit, okay, signals from the receiver something is wrong. But eventually the timer is going to fire as well. So that packet is going to be retransmitted. It's just that, hey, with these situations, we're just, going to wait. So we'll just always wait until timeout. How do you like that? How do you like that? Yeah, so Polly has actually posted a pop-up quiz, okay, on the live chat. It's asking, do you like that RDT 3.0 sender does nothing even though that a duplicate ACK is received? That is saying that the data sent earlier to the receiver is already corrupted, right? So obviously, hey, you just resend. But RDT 3.0 sender, just wait until timeout. And that's going to be slow, isn't it? So do you like it or not? Let me know. Okay, post it down the live chat. Okay. And as you are providing input, let's go on to check a few examples. Okay, given that you know how roughly RDT 3.0 work. Let's go through a few examples. The first video here, about 2 minutes, just are the 3 simple examples. Okay. Now I'll let you ponder how you like RDT 3.0. In the meantime, let's move on and see a few examples of RDT 3.0 in action. So scenario number 1 here is the no loss scenario. So everything is going well. Data, ACK. So you see, packet 0 being sent, receiver here receive 0 and send back ACK 0. ACK arriving at the sender side, receive what? Move to the wait for call from above for packet 1 state. So send packet 1, ACK 1, send packet 0, ACK 0, and go on and on and on. So this is a very straightforward scenario. Now the second scenario where we begin to see packet loss. Packet 0 go, ACK 0 comes back. Packet 1 goes, but dropped. So what's going to happen here? The receiver is not going to receive anything. And the sender side has a timer, right? So that's going to tick, tick, tick until, timeout. Resend packet 1 and restart timer. So ACK 1 comes in. Hey, there's a timer going on here, but because ACK comes in before the timer fires, so that timer gets canceled. So packet 0 go, ACK 0 comes back. So this is the single packet loss scenario. And the third scenario is the ACK loss case. So packet 0 gets out, ACK 0 comes back. Packet 1 goes, and ACK 1 get lost. What's going to happen there is the timer for packet 1 is going to tick and tick and tick until what? Expiration. So this is going to trigger packet 1 being resent, and finally ACK 1 gets received, and data 0 being out again. Now what's a bit unusual here in scenario 3 versus 2 is that, packet 1 was actually received already, but it's received again because the ACK was the one being lost. Okay. No worry, because this is packet 1 and this is packet 1. For 2 consecutive packets carrying the same sequence number, receiver will not extract data and pass it further on. Receiver just send the ACK back again, okay? And that's going to clear packet 1, and therefore packet 0 can go on further. All right, so those are the simpler case, right? Obviously, okay, no loss and either data or the ACK loss. Now the fourth scenario, okay, this is a trickier scenario, and at the end of the scenario, you will see, okay, between so sender there, as I asked in the pop-up quiz, and I see that many of you actually like that the sender waits until timeout and then retransmit, except Junhan, right? Because one will need to wait longer. The sender actually waits longer than necessary, right? So if the sender can just send the data quickly, right, the receiver will be able to clear and then pass the data up to the application. So in a way, retransmitting faster, okay, allows the application, the users, feel that, hey, it's lower delay, right? So it could be a good feature for some applications. Okay, so this last scenario, you will see, however, that delaying the retransmission has some advantage, So whether you delay or not, it's actually a trade-off between time and consumption of bandwidth. Scenario number 4 is to illustrate this case, premature timeout. So that is when the timeout interval is this long, but the ACK and data takes a long time to take a round trip back. All right. The scenario goes like this. Packet 0 goes, ACK 0 back. Packet 1 goes, ACK 1, takes longer than usual to come back. So at this time point, timer expires and packet 1 here gets retransmitted. So packet 1 gets retransmitted before ACK 1 can come back here. Right. So when packet 1 gets retransmitted, timer for packet 1 is restarted. But the good thing is, hey, ACK 1 actually just, arrived. So from the sender's point of view, what's going to happen there is sender thought, ooh, ACK for the packet I just sent has arrived, so cool. Cancel the timer and send the next packet. So packet 0 goes. And that's going to trigger ACK 0 and come back. And data 1 goes, ACK 1 comes back. Data 0 goes, ACK 0 comes back. All right. Well, I hope it's just that easy, because we are actually not yet talking about when packet 1 arrives at the receiver, what's going to happen? Well, receiving packet 1, and receiver there will see this is a duplicate because I just received packet 1, right? So this is duplicate. Ignore it. Don't pass it up to the application layer, but still generate the acknowledgement to ensure that the sender is notified. So ACK 1 will travel back. Now, sender here received ACK 1. That's right after packet 0 is sent. What does that mean? Well, the sender there receiving a corrupted ACK or an acknowledgement that's not quite in sequence number that's expected, then it's probably a negative acknowledgement. So corrupted acknowledgement, negative acknowledgement, that should trigger retransmission in version 2. But in RDT 3.0, what do we do there? We actually ignore it, right? So some of us are not very comfortable about just simply wait until the timer. But you see here, hey, this will actually not trigger any further packet being generated. Okay. You'll see an advantage in the next scenario, where if we run RDT 3.0 with quick retransmission when there's ACK corruption or negative acknowledgement. So you see here, delay ACK, timeout expires first, packet 1 goes first. And ACK 1 there generates packet 0 to go, and so on and so forth. Okay. So this generates ACK 1 to send. But if, we are not running RDT 3.0, but an RDT 3.0 with what? Retransmission upon corrupted ACK or a negative ACK, then we send what? Packet 0. Okay, again. Because obviously packet 0 is corrupted, therefore we get ACK 1. So retransmit packet 0. And that's going to trigger another ACK 0. You see, packet 1, ACK 1, ACK 1, packet 0, ACK 0, ACK 0. So for every data packet, for every ACK packet, there's going to be what? A parallel sending, duplicate of it. Is that good? Even though we try to retransmit early. Not that good either, right? Comparing this case and the previous case. So a trade-off in the design of RDT 3.0 there. Okay, we thought that, hey, delay everything till the timer expire. It's not that smart, but we ended up saving bandwidth in the end, even though the retransmission is a little bit late. All right. So hey, you guys like the mechanism because it's simple. Okay, but there's a performance-based reason, okay, performance-centric reason, because otherwise it's going to generate multiple of these ACK packets, okay, transmitting in parallel. All right, so that was RDT 3.0. We're supposed to do quiz 20, but we had too much fun working on quiz 19. I think that is perfectly fine. So tomorrow we'll start by going through quiz 20. All right, with that said, I say bye. See you tomorrow. Yeah, again, I see that many of you like RDT waiting, okay, for timeout to retransmit to make things simple. Okay, bye. The world is complicated these days. Yeah, I can see. Okay, I would also like things being simple.